Hello everyone, welcome to the lecture of Power Electronics. Myself Amuthini, I am working as an assistant professor in EEE department, Lord's Institute of Engineering and Technology. I have divided into 4 parts of my outline. The first one deals with the introduction, the second part will be power semiconductor devices, and third part will be power electronic converters, and finally I will conclude with the applications. So before entering to the course, I just want you to know what are all the prerequisites needed for this subject, and those are circuit theory. From the circuit theory, I will be using KVL and KCL, and also you should know the behavior of inductance and capacitance for the AC excitation as well as the DC excitation. So we should know the concept of basic electrical machines, power system, power semiconductor devices, and analog and digital electronics and control theory. So power electronics, it is a very interesting subject in electrical energy, and also it is very easy to understand, and it is very important in case of a research. So it is a multidisciplinary courses. Why we are calling it as a multidisciplinary courses means this is the one subject deals with the many subjects, like already I said about the prerequisites. So coming to the introduction, so why we need a power electronics? So if you talk about the power plant, so I'm taking a power plant which I can burn the fuel and I can generate the electrical energy. If you see this block diagram, so from the fuel I'm taking for 100 kilowatts, but 65% of energy getting wasted in the front end of a turbine itself. So only 35% only we are getting output from the turbine, and it is given to the generator. And we know the function of the generator. So generator which converts mechanical energy into a electrical energy. So the output of the generator will be given to the transmission line. So through the transmission line we are giving to the load. So if you see the overall block diagram, so from the 100 kilowatt energy, only 16.5 kilowatt only it is reaching to the load. So the remaining power will be getting wasted in the turbine itself. So the question may arise, so why I am wasting much time? There is a more power losses in the turbine side. So I have to look for another possibilities how to increase the efficiency of the system. So let us talk about the energy scenario in India. So 87% of our energy we are getting from the fossil fuel. In that 70% we are getting only from the thermal power plant. So another 6% we are getting from the nuclear energy. The rest we are getting from the renewable sources like solar, wind and tidal. So from the IEEE journals, it has been projected that natural uranium expected to be last for 50 years, and similarly oil will be expected to be last for 100 years, natural gases for 150 years, and coal for 200 years. Again, one more question will arise, what will happen after 200 years? Whether the civilization will come to a halt or what. So we have to do how to extend this period. So by using 3 methods we can achieve it. So one is using electrical energy in an efficient manner. So the second point, we can improve the conversion efficiency. Here the power electronics will come to the picture. So using the power electronic circuit, I can improve the conversion efficiency. We will be dealing this point in this course. And the third one, we can improve the percentage of the renewable sources. So these are all the steps we can take to avoid the energy losses will be lasting in the few years. I would like to share 2 examples with you regarding the power electronic circuit. So the first example is fan regulator. So if you see the conventional fan regulator, you can see the first circuit diagram. So there are the resistors are connected in series to control the speed of the fan. So if I want to control the speed of this fan, I have to adjust the knob from 1, 2, 3, 4, 5 like that to change the speed of this fan. So what is the problem in this conventional regulator? It looked big in size, it need a heat sink because you are having a resistance, and also it is triggered and the efficiency will be less for this regulator. So we are replacing this conventional regulator by using the power electronic regulator. So the next image we say that you can see this is the power electronic based regulator. The triac will be used as a switch in this to control the speed of the fan. So this will be mounted in the switchboard itself to control the speed of the fan. The next example will be like a mobile chargers, what we are using in everyday life. So the first thing, how we are converting the AC supply to a DC one to give the DC input to the batteries. So here you can see through the step down transformer, I am converting the AC to step down value of a AC, and next you can see the diodes are connected here. This is nothing but the rectifier which converts AC to DC. So again the DC what I am getting from this diode rectifier, it is like uncontrolled one. So I want to have a controlled output of a DC. That is why we are having like DC to DC converter here. It's nothing but voltage regulator. So the output will be 5 and it will be applicable for a charging applications. So this is also one application of your power electronics. So coming to the conclusion, why power electronics? So in order to save electrical energy, we should need some power processing unit. It should be placed in between source and load. Why we are having power processing unit means to give a required input to the load to increase the efficiency of the overall the system. So see the block diagram here, the input is the source and I am having a power processing unit in between and I am having a load here. Here you can see the another block which I added is a controlling part. Like power electronics is not only deals with increasing the efficiency, it also controls the flow of your electrical energy. So here you can see I am taking V, F and I as a controlling parameters, nothing but voltage, frequency and current. You can choose any one of these parameters as a controlling element and you can have the control, and the controlling output will be given to the power processing unit. The power processing unit is nothing but the power electronic circuit. It may be like a rectifier, inverter, chopper or AC voltage regulator. Then next I would like to talk about what is power electronics first of all. So the power electronics means in the name itself you can see there are two parts, power and electronics. We know electronics, it deals with the low power ratings, and power we are talking about high power ranges. So it normally combines three parts, power, electronics and control. Coming to the power, so power it is deals with static and rotating power equipments what we are using in generation, transmission and distribution. So electronics it deals with the circuits and devices what we are used in the circuit, and the control it deals with continuous and discrete control. So how can I define power electronics? The application of solid state electronics for the control and conversion of electrical power. So the main goal of a power electronics is to control the flow of energy from source to the load. Next, let us discuss about the power semiconductor devices. So power semiconductor devices, as we all know about the semiconductor devices which we already studied in the previous semester. So the semiconductor devices which will be used in an electronic circuit. If it is power electronics, the semiconductor devices, it should be operated in a high power applications. So that is why the name it is called power semiconductor devices. So in an electronic circuit, the semiconductor devices, it will be used in a active region, that is a linear mode. So for the amplification process that will be used there, but in the case of a power electronic circuit, those semiconductor devices will be operated in the saturation mode and commutation mode. It's like on and off control only. So one thing you should remember, the semiconductor devices what we are used in the power electronic circuit, that will be operated as a switch only, not in the case of amplifications. So we are having three types of a power semiconductor devices. The first type will be power diodes. The diode is an uncontrolled device. That means whatever the input I am giving, that same will be coming as a output. I may not have any control on the diode. If you are coming to the next type, that is the transistors, and the third one, it's about thyristors. So these are all the basic types what we are having in the semiconductor devices. So coming to the power electronic circuit, so this is the main part of the courses. So types of a power electronic circuit, we are having 6 types. So in that I'll be covering the 5 types in my video lectures. The first one will be like a diode rectifier. As I already said, the diode is an uncontrolled device, so I can also call it as an uncontrolled rectifier. So AC to DC converter, this is called a rectifier. Here I may have the 2 types, uncontrolled as well as the controlled rectifier. And the third one, I'm having AC to AC converter. It is nothing but AC voltage regulator. And the fourth one is DC to DC converter. We can also call it as a chopper or switching regulator. And DC to AC converter, it is nothing but the inverter. And finally, the static switches. So let us begin the session with the diode rectifier circuit. So in this lecture, I am going to cover only the basic principle and operations only, not the complete the switching operations. So coming to the diode rectifier, so it is an uncontrolled rectifier. So if you see the circuit diagram, I am having 2 diode in my circuit. In middle, I am having a resistive load. So if you see the circuit operations, so what is the input I am giving here? AC supply. So you can see the waveform simultaneously. So the first waveform what I have mentioned here is the input supply waveform, that is sinusoidal waveform. We can say it is a bidirectional waveform. That means I am having a positive off cycle as well as the negative off cycle. So if you see the output we are getting based on the modes of operation here. So initially the diode D1 will be getting forward biased when you are giving a positive off cycle as a output. So that time the diode D1 will get conducted and the current will be flowing through this resistance and you will get a positive output voltage. And that time if you see the diode 2, it will be getting a reverse bias and it will not be in conduction. So that is the mode 1 operations. If you see the mode 2 operations, see I am giving a negative off cycle as an input. So that time the D1 will get a reverse bias and it will be turned off, and the D2 will be start conducting and the current will be flowing in the same direction. So we are getting a positive output voltage across the load. So you can see the output waveform. So though I am giving a bidirectional input, the output what I am getting is a unidirectional one. So both positive as well as the negative input cycle of waveform, I am getting both as a output voltage as a unidirectional one. That is why it is called as a rectifier. From AC to DC we are converting. Here one thing should be noted, we are using a diode as a device, so it is like an uncontrolled rectifier. We cannot vary the output voltage here. Coming to the next type of a converter, that is AC to DC converter. So here we can see I am replacing those 2 diodes in the previous slide as a thyristor here, because thyristor is a semi-controlled device. So why I am calling semi-controlled device means during the turn on time I am having full control on the thyristor. During turn off time I may not have any control. So if the input is AC, the thyristor will get a natural commutation for the turn off process. If input is DC, you may need a separate circuit to do the forced commutation for the thyristors. So coming to the modes of operation here, the first one, as we discussed in the previous circuit, the positive off cycle, the T1 will be conducting and I am getting a output here. Here one thing it is very important to understand. So it is like we are having one more terminal as a gate here. So I have the control through the gate terminal. So I am going to trigger this thyristor by giving a pulses to the gate. So once if the thyristor is turned on, then I can disconnect the gate signals. So the delay how much I am giving to turn on this thyristor, based on that only the output waveform you will be getting here. So here you can see the alpha what I have mentioned, that is the delay time I am taken. From the alpha only I am generating the pulses to the thyristor and it will be conducting, and this shaded part as a output we can get it. And similarly for the negative off cycle, the T2 will be start conducting and T1 will get a natural commutation because of this zero crossing voltage, and the T2 will be conducting, the current will be flowing through the load and the voltage will be appearing across the load, same positive voltage we can get it. So here the negative off cycle also we are getting positive output voltage. So that is the reason we are calling it as a controlled rectifier. That means by adjusting the firing angle of a T1 and T2, I am getting the variable output voltage as output. So this is unidirectional output we are getting. So coming to the next converter, that is AC to AC converters. So it is also called it as a AC voltage controllers. So here you can see my input is AC, I should get my output is also a AC. So that is why I need a bidirectional switch. So we are using triac as a semiconductor devices. So triac is a bidirectional switch which can conduct in both the direction of your current flow. So coming to the modes of operation, the first mode I am giving during the positive off cycle, the diode will, the triac will be in conduction and you will get a output voltage like this. So during the negative off cycle, if you wanna see, same in the negative off cycle also the triac will be conducting and the current flow will be reverse direction. So that is why you are getting like a reverse output voltage here. So if you can see, the input is also a bidirectional and output is also a bidirectional in this converter. So that is why we can call it as a AC to AC converters. So similarly, so what we see in the previous circuit, by adjusting the firing angle, we can have the control in the output here. So coming to the next converter, DC to DC converters. So DC to DC converters is normally called as a chopper circuit and also we can call it as a switching regulator, and mostly it will be used in a SMPS circuit. So if you see the circuit diagram, there will be using only one switch. It is connected in series with the load. So if the switch is on, what is happening, and the switch is off, what will be happening, that will be the modes of operation here. If you see here, the output waveform what I am getting. So if the input I am giving a DC supply to this thyristor or transistor, whatever the device I am using in the circuit. So it will be conducting and it is connecting the source to a load. So we are getting an output like this during time T1. So what will happen from T1 to T? So I am not giving any triggering pulses to this transistor. I am making it turn off. At the time it disconnects your source and load. So automatically you will not get any output across the load. So the zero voltage will appear in the load side. Again the cycle will be repeatedly doing and you are getting like a continuous output waveform like this. So here you can see the input DC can convert it into output DC. It is a variable DC. So based on the turn on time period, we can have the control time. So the next converter, so next we will see the another type of a converter, that is DC to AC converter. So it's nothing but the inverter. So the input will be DC here and the output will be AC. We are getting variable output voltage as well as the frequency here. So coming to the modes of operation, the Q1 and Q2 will be conducting in the first mode of operation. You will get a positive output voltage as a output. So during the mode 2, the Q3 and Q4 will be in conduction. The current flow will be reversed. That is why we are getting a negative voltage across the load. So that is why we are having a bidirectional output. And from the DC, how we are converting AC, it says. The next one, it is a static switches. So static switches is nothing but the power devices only. It is mostly operated as a contractor or switches in the circuit. The supply to this switch could be either AC or DC. These switches are called switch, AC switch or DC switch. So let us share some applications of power electronics. So heat control, light control, electric motor control and power supplies, vehicle propulsion system and HVDC. These are all commonly used applications. If we talk about the industrial applications, this is the power electronic circuits where we can use it in a motor drives and electrolysis, electroplating, induction heating, welding and arc furnace, lighting purpose. So to talk about the transportation applications, recently it makes a huge trend, that is trains and locomotives, subways, trolleybuses and magnetic levitations, electrical vehicles, aircraft power system and ship power system. So these are all the few examples of applications I have listed here. There are a lot of applications are there using your power electronics. So I just want to summary my lecture. So what we have discussed so far. So I have been discussed the introduction of the power electronics, like what is power electronics and what is the goal of the power electronics and why power electronics and all. After that, I have shared the power semiconductor devices and the difference between normal semiconductor devices and power semiconductor devices and the types of the power semiconductor devices. And then I shared about the converters type, the power electronic converters. So the major 6 type of converters we are used in the power electronic circuit. In my next lecture, I will be discussing the new topic with you. Thank you.